So thanks to you all. Our club has been making some strides. I have a couple of announcements. Um, the first one, we are now officially a chapter of NAR, National Association of Rocketry. And yesterday, we had CS Department's demo day, and we won the first prize. What that means is our GNC project is supposed to be the coolest project in the undergraduate in CS Department. So let's. And here's a certificate if you guys don't believe.
Receipts. Yeah, we can clap for it too. Damn. So that's what it looks like in person. The craziest part is you should have seen the prizes that we got from that.
Yeah.
Really impressive. I thought that was a prize.
My bag got lost. They gave us a bag, and in that there was a Bluetooth speaker and like some other stuff. I don't remember, but my bag got lost the same moment.
Yeah. Damn. Dude, I just remember like, no, like someone like that was cleaning probably took it.
Yeah.
Sure, I would too.
Whatever.
They don't take a rocket. Yeah, true.
And so right now the current state is the PCB and supplies for building level 2 rockets. By the way, we have how many level 1s? I think about 8 level 1s, right? Yeah. So congratulations for that too.
I think we're all level 1 in here.
Right? Yeah. The room full of level 1s. Okay. And for level 2, they're pretty expensive. So this semester we have pretty tight budget. Hopefully next semester is going to be much better. But we can only afford 3 level 2s. And all the people who are staying at GSU for like at least a year, like those people will be a priority. Like my top 3 contestants are AY and Kubra, because VJ is graduating this semester. Chisholm will be graduating next semester, and he's going to be the president of Robotics Club, so he will have a lot of duties. And Brian, I think you are also transferring for this semester, right?
Yep.
So that's the plan. And the level 2 launches will be on May 10th. So we don't have a lot of time, but we do have like at least 2 weeks. And we will be participating in University Student Launch Initiative competition by NASA. For this competition is a year-long competition. The deadline for registration is gonna be this fall, I think November, around November. But yeah, so we will be participating in this. And this is the final state of how our AVO Mark 1 looks like. We didn't have 3D renders or the 3D models of ESP32 and the GPS and the SD card reader, but everything else is here. And I'm pretty proud of this. And this is the official certificate from NAR. I do have a bunch of updates. So NAR, like being a chapter of NAR, gives us some privileges. For example, we can apply for their scholarships. They have pretty cool scholarships for people who are active. And they also, they can also give like up to $250 per chapter, which is almost nothing as per our budget. But that is something, like it can at least get us one more level 2, one more level 1, I guess, or it can get us a level 2 rocket engine. So, and this meeting is supposed to be a collaborative meeting between the Robotics Club and the Rocketry Club. And we do want to dive into competitive robotics, and I do have a plan for this. And Chisholm, do you want to do?
Oh yeah, just
the opening?
do a little short presentation.
Yeah. If you like, do you want to share your vision, like any thoughts about the club? And also congratulations for becoming the president of.
Oh, thank you. Alright. So my name's Chisholm Maxwell. I'm projected to be the president of the Robotics Club next fall. As Varun said, I'll be graduating that semester, but I want to end my time here at GSC with a bang. So I have a plan that we'll basically get the Robotics Club up and running. Hopefully, we can be able to have participate in competitions. So while brainstorming, I discovered something called Lunar Robotics, which is basically a competition that occurs in that's joint collaboration with like the University of Central Florida. And in this competition, basically you build lunar robots that can mine on the moon. You're given a large field to work with, and you have a year to plan. Now, obviously, it can't stay for the whole year. However, during the summer and during the fall, we can plan and create. We can basically plan very, very well and create something tangible that can be tested. And although we don't have engineering, we have a really large computer science base, so that can really help us get to where we need to be. So my main plan for next semester is getting signed up for that project, and also work with GNC with Rocketech GSU, which is as well as already mentioned, won us the undergrad. One is the undergrad and the demo day, and it's really an ambitious project. And I feel like robotics can be really useful, at least getting this into making this into something incredible for GSU. So that's what I want to present today.
And I want to like continue this one. So I want to continue. So the GNC to the Moon project right now, kind of like leads to something like that. It is like unlocking the space to us. But let's say we have the rocket, we have, let's say, a car to travel there. What are we gonna do there? You know. Then comes the robotics. We're gonna deploy robots, make a base, and then we will go there ourselves. So the Lunabotics competition is like the sweet spot in the collaboration between the Rocketry Club and the Robotics Club. And we will be collaborating at least the remaining semester and the summer semester on the GNC to the Moon. So the resources from Robotics Club, like the monetary resources, they have some budget for this financial year, which we need to spend ASAP. We only have, I think, one more month left to buy the supplies that we want to buy. So we will work on that. Yeah, that's the general directions for the collaboration, and we'll move on. Right now, I think the only board member in the Robotics Club are you, right?
Yeah, basically.
And we're looking out for new leaders for that club: vice president, secretary, finance director, and marketing director. I will just quickly like go over the history of this club. So Robotics Club was started in, I think, 2018 or something, 2019, and maybe later than that. But during the COVID years, like there was no activity, so nobody re-registered the club, and it died off. And I think it was revived by Holly Wallace. She is in Georgia Tech right now. She took transfer. While she was here, she did a pretty great job at actually building a robot. She built a robot which could travel in the campus and collect like pollution sensor. It had like air quality sensor, ultrasonic sensors, and I think it had some SLAM algorithm, some sort of navigation algorithm. And it could basically collect air quality samples from different areas in the campus. And this was their first project, and they had like fantastic funding, because they had the trust of the CS department, and robotics in general is like more trustable than rockets in the eyes of university, because rockets are riskier. So they have like generous funding. But like eventually when she transferred off, things started to fall apart. There was no new robots being created, no new real passion for engineering. Leadership diluted, and I wouldn't like down talk anybody, but there were some clashes. I was like pushing people that hey, let's do something, because so much after having so much funding, you were wasting that resources, all those resources. But now I believe that Chisholm is gonna change things for the better. and we will try our best. When we leave here, when we leave GSU, we will make sure that there's a sustainable system, that new leaders are coming in, new people are coming in, and the generational knowledge is like being passed on. That is very important, and that is very hard to do. Okay, as I said, like we have, I think, more than $10,000 of funding remaining that we have only a month remaining for to like purchase the supplies from. Right. So, what is the current state of the Robotics Club? The Discord server is pretty dead.
It is.
The last meeting was held, I think, more than 365 days ago. Probably like 400 days ago. Don't exactly remember, but so this meeting, like we forgot to, didn't forget, but like the management of like actually hosting the meeting wasn't there, but we still wanted to host a robotics meeting, so we just like said that let's just not make any more excuses and let's just host the meeting. We'll record it, we'll post it out, and from next week, we will have a proper place for the meeting. We will have proper agendas and everything. And we will invite a lot of people. Right now, our goal, as Chisholm mentioned, is to win Lunabotics 2026. And Lunabotics is not an easy competition. Like you're making a lunar robot which will go and mine on Moon and do some activities there. Right now, our club is starting from scratch. We don't have any experience of robotics. We don't have any victories under our belts. But there are some universities, like University of Alabama, Iowa State, San Diego State, and University of North Dakota, that has a pretty good track record, and they've also not just like participated enough, but they also have some victories under their belts. So we can like talk to people there in those clubs to like quickly learn things and get off the ground. All right, now let's come on to the actual agenda of today's meeting. So my goal was to like give you guys an overview of, let's say you had some imagination of a system that can like probably move from a place to another place and probably like pick some stuff, like do something. Let's say you had this imagination, right? For any specific application, it could be like a surgery robot or whatever like crazy ideas. Now, how would you actually make it in the real world? That is the motivation for today's meeting. So there's 4 black magics. If you know how to cast these spells, you will be able to almost build anything that your imagination allows you to imagine. And the first one is microcontrollers. So let's talk about microcontrollers. Does anybody know the definition of microcontrollers, or like anything about them?
I mean, I kind of know, but it would be like, basically it's like, is it basically like a system, like it's like a mini computer that specializes in specific tasks? Like a processor.
Yeah, it is a processor. Yeah. Good. Like anything else? Okay. Like what can you do with it, or what are the possibilities that you can do if you had a microcontroller and if you knew how to use it? Does anybody know?
I know, like you can control motors, control like move data from like power sensors. You can use it to like control a GPS module, I guess.
Like I'm pretty sure you all have heard about Arduino. So Arduino is like the most famous microcontroller out there and the easiest to use. What you can do is you can buy an Arduino, plug it in your laptop, write some code to like blink an LED. Like that's the first program that almost like all people write And we have like a bunch of other ones also. For example, the one that we use in our flight computer is called ESP32. We also have, I think, around 10 STM32s in our supplies that we never got to use. And then there's new generation of microcontrollers coming in as we speak, which are based upon RISC-V architecture. So I'll define microcontrollers a little bit. They are ICs or integrated chips, or you can go with like a more general definition. Imagine a CPU or a central processing unit that can do any generalized computation. So any program that you can write, technically you can compile it for a CPU, which is a generalized architecture. So there's a lot of abstractions here. I don't think we should like dive in all of them, but CPU I think is a pretty understandable or interpretable definition. And the like ESP32 is in itself like just a small chip, but we don't just use that chip. Like one clarification I want to make is we use a module. It is a breakout board that uses that chip. That breakout board allows us to like have pins, like bigger header pins that we can like connect things to, and it also have other chips onto it. For example, a crystal oscillator, which generates the clock signals, and it has a flash memory chip on it, which is a volatile storage, and it dies off. But as long as the thing is powered, you can store things on it. And there's a lot more chips, and there's communication chips. There's power ICs, which takes in some different voltage. If there's noise in the voltage, it balances it out and stuff like that. I want to start talking about voltage signals and pulse width modulation. Vijay, do you know? You know pulse width modulation, right?
I mean, only like somewhat, you know.
Do you want to like talk about it a little bit?
I mean, from what I understand, like a certain like quantity of a certain length and pulse will equate to some like actuator output. I think I don't know like how it's generally structured. Is it like on the number of pulses within a region or like the length of a single pulse?
I'll go a step back and I'll define what a signal is. We should all have an intuition. When I say signal, like what picture comes to your mind?
The square wave?
Yeah,
The square wave?
some sort of wave.
Yeah, like a wave, like the Wi-Fi symbol.
I see.
Yeah.
So a signal could literally be in any form. Usually it is something that changes over time. Let's say there's a ball in water, and water is like going up and down. Then the ball itself, like ball's position is a signal. If something is getting brighter and then dimmer over time, then the brightness of that thing is a signal, right? So some information that changes over time, or any parameter that changes over time, is a signal. And when I say signal, in this context, would mean a voltage signal. It will always be a voltage signal. And I will define voltage in a second. Brian, you're taking electromagnetism right now, right?
Yep.
Can you define what voltage is?
It's change in electric potential energy.
Like the actual formal voltage definition?
It shocks you when you touch it. That's what you know.
Okay. So imagine it is like some quantity we don't know about right now. We will see what it does, and then we will build intuition from there real quick. But let's say here on the x-axis, I'm calling time. We start from t equals 0, and as time progresses, we, let's say, are plotting the voltage. Now you might be wondering, like, voltage of what? You know, like what is voltage associated to? It is associated to the space-time. So in physics, like we have something called electromagnetic field. In that field, we define a scalar field, which is voltage. So voltage is not a vector; it is a scalar, and it is kind of like in this. Let's talk about this room. In this entire room, at every point, there is a number. That number, if it is all zero, then there's no voltage gradient, then there's no electric field. But if that is not zero, let's say where Brian is sitting, let's say there's higher potential, like the numbers in that area that correspond to voltage are higher than where I am standing, then there's going to be a gradient of the voltage, right? What this gradient will do is it will push any charges in this volume. So what voltage is a parameter or a physical property defined by physicists that is used to then describe like how the charges are facing any forces. Because the gradient of the voltage, which is a scalar field, describes the amount of the magnitude as well as the direction of the force that applies on the charges. And like it might be very abstract for the first time, but hear me out. So I don't want to like go in deep in physics and equations because I have to like explain PWM, what the pulse width modulation is. So I will keep it in the context of ESP right now. That is what we use. Let's say this is the main chip. This is the USB port. And let's say these are some pins. Now let's say we are checking the voltage at this pin. So this pin is like, as I said, like voltage is something that is in the space, not on a pin. It is in a space. So why am I saying that we are measuring the voltage of a pin? Pin is metal, and metal is a conductor, and what conductor does is throughout a conductor, the voltage is constant. That is kind of like the magic of conductors. If let's say there is a metallic tube, and I increase the voltage here, let's say plus, minus, let's say there are more positive charges on this end than on that end. If this is an insulator, it will stay like that. But if it is a conductor, these charges will redistribute even out. And they will even out to a point when the voltage inside of a conductor is literally like perfectly evenly distributed. And now, like if you remember, if it is perfectly evenly distributed, there is no gradient. Voltage is not changing. Now charges will stop moving. There is no one to like push those charges anymore. So even though voltage is a property that is described in like free space, we can say that in a conductor, it is constant everywhere. So let's just read what the voltage on this pin is here. It will tell us like whatever is happening to anything that is touching this thing. So let's just see, let's say you want to create something like that. Let's say to control some motor, you want to generate this signal. How can you actually generate a signal like this? Using a digital computer. So a digital computer do not understand anything, but it only understands 1 and 0, or any two values. It could be 0 or 0.5. It could be any two values. Now, how do you actually like generate, for example, these values then? Because these are neither 0 nor 1, right? It is not just almost impossible, you literally cannot do it. So we have to like figure out a way to mimic this behavior, because there's a lot of applications where these like either 1 or 0 is not going to suffice you know. So what do we do actually is we say Also, like before that, I wanna say, let's say the frequency at which the computations are happening in ESP is like 2.4 megahertz. What this means is like at every second there's 2.4 million clock cycles. And let me just like, let's say this is the first clock cycle, this is the second clock cycle, this is the third clock cycle, and so on.
I think it's a good idea to explain like what clock cycle is.
That would be like too much. Like I can like keep talking about it, but like you will like go nowhere.
Oh, okay. I'll just say like a clock cycle. Just to be really simplified, like a clock cycle is basically like each step in which a computation happens. Basically, like a basic computation happens at each time step. That's a clock cycle. Yeah.
Right.
Just to be like brief with it.
Just to give more clarity on that,
Mhm.
there's a cycle called computation cycle, and then there's a clock cycle. So clock cycle is literally a square. A clock signal is a square wave, equally distant peaks and troughs. This is happening with the clock. So using this, CPU triggers its events. If the voltage drops, for example, this is detected by the CPU, and it does something to its registers, and something happens. And 4 of these combined, like 4 events, is equivalent to 1 computational cycle, because like you will see this in computer architecture classes, because there needs to be 4 different events to make for 1 computation. Okay, so let's say these are the clock cycles, and what we want to do, or let's say these are the computation cycles. What we want to do is we want to create something analogous to this. One way to do it is let's divide the whole time into like discrete chunks of some cycles. Let's say we want to do it discrete chunks of 4 computation cycles. It might, like, just hear me out. 6, 7, 8, 9, 10, 11, 12. So what I'm saying is like we're gonna split this in these discrete chunks. Okay. So if you want to make something like this, let's just focus on this area, like just only in the increasing area. I'm gonna recreate this effect here without ever, only by using like either 0 or 1.
You draw a line through it so that way you know.
Let me just change the color. So what?
Like you can draw a line from the 1 all the way down there.
If I did that, then it will be like that. That is not what we want. You know what I'm saying?
Yeah.
But if I did this, it's a good sound effect. And then the next peak will be even longer. See what I'm doing here?
Yeah.
Like here, in this chunk, the amount of time we're positive, or amount of time we're 1 is 0. So there's almost like no energy here. But here, there's a little. Here, there's more. Here, the board ended, but like there would have been even more. So like we're splitting it and using just 1s and 0s. We're replicating what is happening here. So this is pulse width modulation. You're replicating an analog signal. This is what we call analog, because I mean this is just the definition of the word. If you can go between values, between 0 and 1, then that is analog. You have like continuous space, output space. But here we only have discrete. We call it a digital, and we can replicate analog signals using digital signals, using by modulating how how wide our pulses are. So we split the whole signal into discrete pulses, and we modulate the width of those pulses to replicate these behaviors. If I just like shade the positive area, and this is not working.
So you're saying like basically representing an analog signal with a digital signal.
Yeah. Because once that is clear, we can move on. Yeah, I would just stop there, I guess. We have a lot to cover. You can see the slides, right?
Well, see the slides?
Yeah.
Yeah, we can see it.
So did you write some documentation on programming? Sorry. On programming these controllers?
Yeah, I mean, in just like my specific branch of like HPR level 1, like I had like an avionics like overview on like how different library files work, the communication protocols, and how the CPP is interacting with this through like the SD card, and then like I gave like a paragraph about like event detection too.
Okay, so BJ had written some documentation that I'd recommend you guys to read about. It is just on basically how you actually like program it. We stopped using Arduino IDE because that's for boys, not for the men. But that is very limited. So Arduino IDE was not sufficient for us. The reason for that, our software is like growing by the week. So we need something where we can manage our software much nicer. I will quickly show that 1.3 here. And Visual Studio Code is a really nice IDE. You can manage things a lot better. This is some serious embedded development. Thanks to Platform.io, this is an open source platform that you can use to program any embedded system. We call microcontrollers, by the way, embedded systems. There is no operating system on that. So whatever program you do, that program is literally ones and zeros that you embed on that system. So VJ wrote some documentation you can read, and I already had some documentation beforehand on at least the setup of it. Like how do you actually set up this Platform.io, how you connect the ESP to your laptop and do stuff like that. Kubra can also help you with that. I think now you understand fairly good enough, right? Like at least the setup. And she had also contributed. I forgot the exact. I think it was magnetometer.
It was it. Well, I think she did MPU 9250.
Oh, that's even cooler.
Nice.
So she wrote a library for MPU 9250. This one.
That's the new sensor we're using?
Yeah. This
Oh,
is
nice.
This is. Let me just show you. This is this sensor here. Amen. These purple sensors. These are MPU 9250s, and Uber wrote a library for these. What we do is like we have all the libraries here. We import them in the main flight software. This is the older one. I will show you the latest one. Yeah, event detection. So this is our latest flight software that flew, and it actually detected all the events perfectly, except for the landing. But landing is not a sensitive event. The critical events are detecting the launch itself and the apogee, and those were perfect. And this code, as you can see, is already, I think, 400 lines, more than 400 lines. And this would have been, if we were to like write this in Arduino IDE, we would have a single file with like 1,500 lines, and that would not be manageable at all. That is why we shifted here. We have the libraries up here. We add different functions. We keep changing them, and the main flight software is still pretty manageable. Also, that's another success for the club. On the first try, our event detection actually worked. And we were thinking the whole time that it never worked, but it literally worked. And the problem was that the print statement was not in the not in a file it was supposed to be, but it actually like snuck into the actual data, into the flight data.
Oh, so the print signal was in the flight data.
Yeah.
Oh,
And later we figured out like, oh shit, there is landing detected written in the CSV of the main.
Hey, at least it works, man.
Yeah. Okay. Yeah, we'll move on from here. Let's go to the sensors. Do you guys know about any sensors or like anything in that direction?
Like specific
Like-
sensors or
Like if you know the names of any sensors,
Motion
or if
sensor.
you, yeah. Do you know like what kind of motion sensors are there or how they work?
EMC security. I know they work by, they have like, they cover this, like a limited amount of space, and once you get within its proximity, then like, there's a light that beeps that shows that, oh, it senses motion.
And do you know how the proximity is measured?
I do not.
Okay. Does anybody know about any other sensors?
Yeah, I don't know any of the names.
GTU7. Was that the pressure sensor?
Not even the names, just like if you know, like for example, how GPS sensor work, or
Oh, I know it uses a protocol called like MNEA or something like that, and basically it uses like satellite, like satellite, like trigonometry, but some like satellites to like pinpoint where you are. So like, I learned this like while like testing out the GPS as well. For example, if I'm in a room, like for example, we were testing it inside the X lab, we weren't getting any information. We were getting a little bit that was able to like peek through, but we got better information when we went outside. So like that's how, I don't know exactly how it receives the information from the satellites. I just know that it does. That's all I know.
so the goal of most sensors is to like measure some voltage that is coupled with something. So for example, if I'm talking about an accelerometer, if let's say my hand has an accelerometer and I do this, when I accelerate it towards my left, what happens is there's some capacitors that are like interlinked like this, and one of them is fixed, but other one can like hang in there a little bit, like it is like free to move. What ends up happening is like it gets closer. So let's say this was the fixed one, right? The fixed one will move because my hand is moving, it is fixed on my hand. But the other one, which is kind of like free floating one, will be pushed back. It will like almost come closer to. So what happens is like the capacitance between these changes, the distance changes. I will now quickly talk about capacitors in the setting of voltage. You have another board?
It's over there.
Wait, does it have a back on it? We can like turn the back on
Yeah,
it.
you just erase it.
Oh, never mind.
Yeah, that's fine. Okay, it's fine.
Poor BJ.
It's fine.
Did you want us to warn you if you go over a certain time or something?
Oh,
It's like 6:38 now.
and when do we start?
I have no idea.
I think it was around 6ish.
Started at 6.
We have some time. So I think we're going pretty good.
We can just edit it down, worst case scenario.
Yeah. Okay, so let's talk about charges and capacitors. So, Brian, do you want to like talk about what a capacitor does?
It just stores electrical charge.
That's
Um,
right. And how? You know,
C equals Q feet something. I don't know.
like what do you do to the capacitor plates to actually charge them?
So look something like this, right? There's two plates right here, and in between them there's some sort of material. I've got my notes in them, so you give me a second. I don't whip it out.
Even if there's nothing, like, they will still store the charges, so.
Yeah, but typically there's always something in between them. Be it air, which is something.
Yeah.
Oh, something with capacitance?
Like, do you wanna talk about, like, what do you do to a bare capacitor to, like, actually charge it?
Yeah, you just send the voltage. Well, you're sending current in there, and then it gets stored into here, and then it releases it, which is like some sort of time constant, and that was dictated by that. Give me a second here because I have it on here.
Yeah, basically,
Okay. Yeah, so these two plates.
okay. We didn't see that.
Yeah, I was meant to see that. Alright, so these two plates are called electrodes, and then the inside,
Now everyone's awake.
on insulator. Also, it's a die.
Oh, yeah, because it prevents them from like discharging.
That
Right.
and it increases the
Capacitance.
capacitance. Yeah.
Because I remember this from like physics too.
Yep. And then we already put this up there. But yeah, this is just the general case of a capacitor.
Okay.
Interact differently depending if it's DC or AC. Alright.
So I think at this point, like, you guys should start taking notes. So I want to like clarify a bit more about like the process that takes you from here to there. So as Brian said, like you actually connect it to some voltage and it accumulates charges. But how, like, why is that? So the reason is, let's say we have a battery. What battery provides it is voltage gradient. This is a schematic symbol for the battery, and the longer end represents the positive terminal. This is just a convention, and the shorter end is to represent the negative terminal, and the wires that you can draw, or just the wires, is just the conductors. So as I said a second before, like the conductors are kind of like magical in a sense. They have same voltage throughout. So let's say that this was 0 volts, and let's say this is plus 5 volts. What's gonna be the voltage of this plate? This plate is also a conducting plate.
Voltage?
Yeah, voltage of this conducting plate.
5.
Yep. Plus 5. And this one,
5. It has to be the same, right? Because
well, no.
Minus 5.
No. This is
0?
0.
Oh.
So it has to be 0.
Oh.
It is a single piece of metal. So there is a voltage difference now between the plates. There's some charges that flew from the positive terminal. Some positive charges like they climbed up, and now they're accumulated on the surface. And there's a voltage gradient. Like, where is it? Now, the question is like, where is the voltage gradient?
In the change between the positive plate to the 0 voltage plate.
Right. In this region, there's a voltage gradient, and then there's gonna be electric field because of the voltage gradient. Electric field is defined as a vector field, which is, so V stands for the scalar voltage field, and if you take the gradient of it, you will get negative gradient of it, you will get the electric field. And how much charge, let's say I put a small charge here, right? Chisholm, give me some charge, bro.
A small one?
Yeah.
Like how small? Like still in voltage or like
In coulombs, like,
coulombs? Minus like 9 coulombs?
okay, minus 9 coulombs, that's a lot.
Wait, what?
But it's cool. Let's say we put in minus 9 coulomb of charge there.
Oh, like 9 nanocoulombs? Is that proton? Well, I forgot what it was. It's been a while.
And those what?
Yeah, I think minus 10 to the minus -9 or something is that, like that's the range of, I think, proton.
Oh, okay. Like,
But it's positive, proton is positive, like, but you, charge on an electron is, I think, -9 point something.
like 10 to the minus something. I know it's 10 to the minus something.
Yeah.
I just know it has 9 in it. That's all.
Yeah. You don't have to remember it.
Okay.
We represent charge, like the amount of charge, usually by Q, this Q symbol, the small q. And let's see like how much force will this be facing? Because we just discussed about it that there's gonna be some force. Like this is where like the black magic actually starts to happen.
Wait, you want me to explain this one? Because I really like explaining this part.
Sure.
Okay.
You see what I'm saying, bro?
I'm going for electrical. But yeah, so for that, we go with electric fields, like a positive charge, proton and electron. So positive charges, they have an electric field that extends outwards. That's an arrow. Electrons, they have a field that goes inwards.
And this is their divergence.
Yeah.
Yeah. But when we have something like this, we can create this, and we can manipulate these fields. So when we have a positive plate, they still follow a positive charge. So they're gonna go this way. We have a negative field, or negative plate, and it's just being attracted towards that. So these charges won't like move closer to each other. They'll just create an electric field, which is a vector, because it's going in this direction.
Right.
When we throw in a charge in there, yeah, let's go. Make it 9. That's a 9 columns. So this kind of goes with just everything. Everything in life for potential energy, it will always go from high potential to low potential. Since it's negative, the negative field, or the negative plate is actually its high potential. The positive side is low potential, because these two will repel each other. So this charge will want to go in this direction.
Positive side is higher potential, right?
No, it depends on the charge, because this is negative, so the negative field, it pushes away.
Yeah,
And it goes against the electric field.
Yeah.
Yeah.
So you were saying like the direction of the force for a negative charge is going to be opposite of the electric field, but if it were a positive charge, it will be pushed in the same direction as the electric field.
That's because positive repel each other, negative repel each other.
Yeah.
Quite the opposite, and they get attracted to each other.
Right. So the crux is like there's going to be some force on this cube that we put here, and the magnitude of that force will be, let me just like label it that this is -9 coulombs. Coulombs is just a unit. Don't like stress about it. The force on this charge q, which I'm going to represent by FQ, is going to be a vector because force is a vector. It has a direction. It will be the electric field in wherever that charge is placed in, the electric field at that point, E, times the magnitude of the charge. This is the force. And if you remember, I just described what the electric field is. It is the gradient of the voltage. Like, by the way, like for Calc 2 people who took at GSU, I feel sorry for you all, but this is, the gradient is defined like this.
Something.
Let's say V is any vector field. I can also call it a simple function, a function of x, y, and z in the space. Looks like this. It is a vector of del f by del x, del f by del y, del f by del z. So I can also like represent it in simpler terms where like del f by del x I plus. This is just a different notation for the vectors. Like these two mean the same thing, right? I'm pretty sure you've seen this one before, but not that one. Right? So these are the same notations. If you're taking linear algebra, you would understand. Yeah. same notation. So what this represents is like how fast is the value function x is changing when you move along the x dimension, the x-axis. Right. So yeah, this is gonna be the force on the charge q, and now we have like some like mechanics of how some definitions that we can use to understand how much force is gonna be there, to understand what voltage is, what charge is. Like we have quantified almost all things. We can use this to like build up motors because we can see how much force is happening, right?
Mhm.
Now like the only thing that remains is current. You don't have any intuition for the current. So let's just also quickly talk about that. Yes, capacitors are done. Oh, I didn't talk about capacitors enough. So here's what I like want to add in the knowledge of capacitors. So what can we do with it? In the terms of signals, and in the terms of sorting charges. Oh shit, it's 6:50. Okay, let me hurry up.
Right.
Want to skip?
No, I'm just like reconsidering like what to talk about capacitors real quick, because everything else is not gonna take too long.
They filter stuff out. We'll talk about that. Use capacitors for
Yeah, sure.
filters.
Yeah, okay.
Oh, okay. Because I was gonna say like how to change your capacitance depending on what you need, right?
Yeah, I haven't defined its capacity.
Oh,
So,
okay.
let's define the capacity of the capacitor, like its capacity to store charge. So the capacity to store charge, let's say it is represented by C. This will be how much voltage difference is between them, between the two plates. Right now we had 5 volts of voltage difference between the two plates. But what if we had some other number? So let's keep it generalized. Let's say it is V amounts of voltage difference. So it is defined as the following. How much charge can the plates hold given V amount of voltage difference? So charge per unit applied voltage difference. This is how you define the capacity of a capacitor. Now think about two capacitors real quick. One of the capacitor can store, let's say, 10 times charge for the same amount of voltage difference than the other one. Now in this case, the C1 that can hold 10 times as much charge will be 10 times higher capacitance than the other one. This is how we define it. This is pretty intuitive. Like if you were the physicist who first time defined it, probably you would have done the same definition. Now let's talk about like yeah. So so we now have a definition to relate C and V, like how much voltage difference you're applying between the two plates, and some quantification for the capacitors. We will use this in the equations that follow, but we're not gonna like dive deep in the equations. What I do want to touch though is the distance between them also matters. Let's say the distance is d. If the distance increases, let's say it gets doubled, did anything change? Like if let's say we have two capacitors, one with two similar capacitors, one let's say 1 centimeters apart, and the same plates, let's say 2 centimeters apart. In these two capacitors, is there any like fundamental difference?
No, because
Yes, there is.
Something with the voltage will change. Voltage has something to do with work, and that's force times distance. So there's distance.
oh, okay, that
The response capacity is more than
That's right. So the closer the capacitors are, the capacitor plates are, the more charge the more charge you can store on.
yeah.
It might seem strange, but there's a reason for it, and the reason is the following. Let's say, so you guys know about like positive charge attracts negative charge.
Yeah.
So imagine like you're bringing them closer. Now like the attraction is getting stronger and stronger. You're not letting them touch, so they cannot they cannot like recirculate and like even out, but the attraction is getting stronger and stronger. You're pulling more negative charge towards you as you bring the negative plate closer. So there's going to be more concentrated negative charge, right? So this Q here, even though the V is same, this Q increases as you bring the capacitor plates physically closer. And there's a relation for that. I will just like, instead of deriving, I'll just like pull it up. The relation looks like this. Here, this is a different formulation. We come out of the realm of like how much voltage we are applying. We check how big the capacitor plates are, and how separated they are, and what is the medium, whatever medium is filled between those two plates. What is its electrostatic constant? We can talk about it like in a physics oriented lecture, but right now I'll just stick to like what we care about. We care about like that C is inversely proportional to the distance between them. If I increase the distance, what's going to happen to the capacitance? Decreases. Perfect. So this is lower capacitance than this one. To be precise, this is as half as this one.
So it's a linear.
Yeah, if you can store like 10 coulombs here, you will be able to store 20 coulombs here. That is what capacitance means. So I want to talk about like coming back to accelerometers. Why does this all matter? You know, when I told you guys like imagine a setup like this, and let's say this is this. Let me just draw it. Imagine like two entangled forks, right? And let's say this is connected to something and this is also connected to something, maybe to an ESP, right? The voltage on, and let's say there's some charges on there. I'm just gonna quickly draw the charges. So this is a +1. And let's say this is the -1. There's going to be some voltage difference between them, right? Because it's the same setup. There has to be some voltage difference here. That difference depends upon the distance between them. Now, if why that? Because now this quantity has to be the same as this quantity, because they both define the same capacitance. If I write that, so here in this formulation, you can see that voltage will increase if the distance will increase. They're both in the denominator. I can simplify this even further if you want, like, just like basically like think about it. If I multiply it, like if I halve this quantity, this also has to be half to stay equal, you know? So they go hand in hand. Voltage will increase if I increase the distance between them. So when I shook my hand, and if this fork right here is connected to my hand, but this is kind of like free to float, their relative distance will decrease. This distance, d, it will decrease for a moment. And that reduction in that distance will be proportional to how fast I'm like doing this motion, to how fast I'm accelerating. And this will cause proportional change in the voltage, which our ESP can read. So there's direct proportionality happening between the amount of acceleration I'm producing, second, the distance d, and third, the voltage. All these quantities are proportional to each other. So if we know one of them, how one of them is changing, we know how all of them are changing. So this is the magic of like sensors, of modern sensors. What we have done is like we've created. This is the exact diagram for a MEMS accelerometer, MEMS stand for, I guess I'll write there. Can you point the camera here for a second? So this is these sensors are actually built on like nanometer scales, like which is like mind-boggling. How the hell do you make these things like so small? We call it microelectronic mechanical systems, MEMS. And there's also other types of sensors. And everything else from here will be pretty fast. I guess I'm gonna like cut this part.
I found it funny how we all get different ads on YouTube depending on what we be searching.
Yeah. They're so personalized.
Yeah.
Yeah, I can tell what Rune's been looking at.
Okay, there's no audio in this. It's messed up. But okay, let's look what is happening here. So we have a laser source. It is generating a laser pulse, which is in the red color, and we have a beam splitter. This is a crystal that lets the laser pass through, but it also reflects some of its energy. So the passed laser is a red one. The one that got reflected is now represented by the green color. We have two mirrors, one final mirror. Well, actually, these are also two mirrors. They come back, they combine using the same beam splitter, the same crystal, and then they go into the detector. Now let's see what's happening here. How can this become a gyroscope sensor? Like it might. So this has something to do with special relativity. So like Einstein level shit.
Oh, really?
Yeah.
Jeez.
I don't know if they explain the mechanism here.
Is this a new thing, or has it been out for maybe like 10, 20 years?
This is like 20, 30 years. Pretty recent.
Oh, wow, that's crazy.
Yeah.
This is what modern gyroscopes do.
Let's say the system started rotating in one direction. This will elongate the amount of distance one of the lasers has to travel and reduce the amount of distance that the other one has to travel. So these two pulses, when they're not moving at all, when the setup is like this, they travel equal amount of distance, they come back, they unite here, and they go into the detector. The detector, if you guys have, I'm pretty sure you've seen like this. This diagram of like electromagnetic waves or like the light waves. So light waves are fluctuations in the electric field, electromagnetic field. What I want you to focus on is, let's say I have two of them, and they're superposing, meaning they're occupying the same volume in space, and they have the same phase. Meaning, what the word phase means here is like, let's say this is the line of the peak of the red curve, and this is the peak position of the purple curve. If I shift them, right, then I'm adding phase difference between them. If I overlap them, then there's zero phase between them. This is how we define the phase. So what is happening here is when it is not rotating at all, and the beam comes together after splitting, after traveling equal distance, this is the situation. They have zero phase difference. They're overlapping perfectly. But if I started rotating this system by omega, right? Let's say I'll just play the animation first, and then let's say it got rotated by omega. Now here, did the red beam travel more or did the green beam travel more? I want you to answer. Which one traveled more?
Red.
The red.
You're right, the red one.
It was going to
No,
this-
hold on. The green one traveled more.
Oh yeah, because.
Let's see it one more time.
Further.
Yeah.
So at the same time.
This is the same one, but here it's gonna be different.
Oh yeah, the green.
Oh yeah, yeah.
So the green one traveled more. The reason is pretty simple. Your this I'll go there. On that board.
Oh, the camera. Sorry, you did.
Yeah, this doesn't work, but when you start rotating this thing, this so there's two distances being traveled by the light beam. This line, but because this line is rotating, what's happening is the rotation is happening about this point. Omega is like the rate of the angular rate.
It's like the angular velocity.
Right. Now this line will be shifted to this point. Now the pulse doesn't only need to travel this distance to go here, but it also needs to travel this distance because like the whole line is shifted due to the rotation. So the eventual distance traveled is this. This is a longer distance than the previous one. So so it is longer for the light that is for the pulse of light that is bouncing in the same direction with the to the rotation. Like if the rotation, let's say, is happening in this direction, and the beam got split about here. Let's call this 1. Let's call this 2. Then here the 1 will travel more than 2. Okay. So let's also I can draw the phase difference here. What will happen is let's say this is the beam 1 while coming back into the detector. The beam in this case, the beam 2 will be shifted towards here or there. If let's say this is the time axis, let's say this is the time axis. I want you guys to predict, will the beam 1 lie on top of this, or to the right of it, or to the left of it?
It's spinning that direction, yeah.
In this case.
And beam 1's taking longer.
Yes, to the right.
So you're saying beam 2 will be to the right of it?
Beam one.
I think beam 1 will be to the left. Wait, does it take beam 1 is the one that travels longer, right? Sorry, just trying to.
Here, yes. Anything that is traveling, that is bouncing in the direction of the rotation, that is traveling longer.
Oh, okay.
So beam 1 is traveling longer. It will, of course, be late at 0.8 seconds. So will beam 2 be ahead of it? Before it, yeah, it's gonna be before, because beam 2 travel shorter distance.
Oh, yeah, that does make sense.
Yeah. Okay. So here, if like you see, if you were to add those two rays, what's gonna happen? They will add crest to crest and trough to trough, right?
Right.
They will end up in a constructive interference. But if this distance is, if you separate these out, there's gonna be somewhat destructive interference. Meaning the resulting wave, if you add these two together, how will you add this together, you might ask? The adding process goes like this. You just literally add these distances. So for example, here I'm going to add this length into this length, and the resulting length will be up here. So the resulting wave will look somewhat like this. Oops. And this, these peaks and troughs will not be as high as in that case, because there's some misalignment here, and you can see this misalignment in the detector, and the voltage will change proportionally to this misalignment, which was changing proportionally to the angular rate, which will tell you how fast your thing is rotating. And again, this also falls under the MEMS category, meaning like it is microelectronic, so it is so small we can only see it under microscope. And the reason I said like this is Einstein level shit is that it is not so easy for like you to do calculations without knowing special relativity, because you're talking in terms of like anything that is close to the light of speed of light. You cannot just like talk in terms of the basic mechanics. You need to consider that time dilates and the space dilates, which is like for another discussion.
It's like film interference, kind of like that.
Yeah.
That was like completely different.
Thin film has nothing to do with special relativity, but it has to do with the interference, of course. Again, then there's strain gauge. Strain gauge are resistor based. The resistance changes based upon how much strain there is on the strain gauge, and because the resistance changes, the voltage also changes. So you can still again like you can chain these relations up, and you can see the results and tell what would have happened to the initial state or to the initial property that we were looking at. I think I did talk about it like probably last semester, remember?
Yeah, just a bit.
Yeah. And we have angular encoders. These ones are probably my favorite. No, I would say like the coolest are ring laser gyroscopes, and the second coolest are angular encoders. There's a bunch of them. Like there's like I think two major types. The first type is called Hall effect angular encoder. What Hall effect stands, I mean, what Hall effect means is you have magnetic based sensors. What you do is like you place a magnetic sensor, and in your shaft you place different magnets. So what you do is, let's say you placed north facing up magnets, and then south facing up magnets. I'll just draw it, I guess. Let's say this is your shaft that is rotating. You will put some magnets on here. Let's say the red represents the north. This is the north side up, and then you will switch the direction. You will place south side up, and you will keep doing it in the whole shaft, right?
Is this like brushed powders?
No, this is encoder. We're still in the realm of sensors. We're not in the motor realm. The drawing is getting horrible. Okay.
So So this is what you just explained on a larger scale.
No, I haven't explained yet.
Oh, sorry.
I just hope that they're even, otherwise they will not line up. But I guess I'll merge them if that happens. Oh, they line up perfectly. Yeah. So, as I said, like, say that this is the north side and this is the south side of magnets. And what is happening here is we have some magnetic field going on from north to south.
I do remember seeing something like that before, maybe on image or because that is so familiar with me.
Yeah, you must have seen that. So here, let's say you place, let's say this is on a shaft that was rotating. That is where our discussion was, right?
Mm-hmm.
This is very small, on a very small scale. You have some magnets on the shafts. What you're doing is you place a magnetic sensor here, right next to it. Probably like, so what the hell is a magnetic sensor now, right? Like, if you know how to sense strain or how to sense pressure, you can put a magnet here. Like, be creative with it. Let's say this is north, this is south. And let's say you put a pressure sensor here, right? I'm just gonna like draw P on this. If, so proportional to like how strong there is magnetic field in here, this magnet will be pushed. And you can relate that push to how much pressure you're sensing on here. Like, you can be creative with all these sensors and you can create like a bunch of other sensors. So for example, like we just created a magnetic sensor. So you will have this, you will be reading how much voltage is coming off from the pressure sensor, and every single time, like, you will have a transition between here. So north and north will repel each other, right? There's gonna be strong repulsion, and as soon as you go to the south, there's gonna be negative pressure or like the negative voltage here.
Right.
So you can sense a signal that is increasing and decreasing as this thing is rotating, and you can see how much rotations has happened. Let's say your magnets, each of your magnet cover, let's say, 2 degrees per magnet, and let's say you saw some rotation happen. You don't know where your shaft is pointing right now, but let's say you know that there has been 10 ups and downs. What does that mean? That means there has been 10 magnets that has been passed, meaning 20 degrees has been elapsed. So you can tell where your shaft is pointing at all times if you keep track of this voltage, if you count how many peaks and troughs has been on this voltage signal. Again, like, this is also pretty impressive. This is like creative application of what we have seen so far. And from here on, like, there's not gonna be too much new. It's just like people being creative, people being engineers. And that's the goal of like the whole meeting today. You can literally be so creative with all these things, all the tools you have. You can create almost anything that comes to your mind. Thanks. Not over. I still have to go over BLDC motors and controllers. I'll just quickly like play this video, I guess, skipping everything.
This is a brushless motor. It is often used for creating lift, and it uses 3-phase electricity. I'm going to show you how they work and even how to control one with an Arduino in this video, which is sponsored by Brilliant.org. A brushless DC motor looks something like this. They come in various
That's
sizes
the one we're
and
trying to use, the
designs,
GNC,
but they
right?
all convert
So we will be using this for the test setup of our GNC project. Instead of using the actual rocket engine, we're going to use this with the propeller on it to propel our rocket, to simulate kind of like the thrust regime that a small rocket engine will provide.
energy into mechanical energy. We can use that mechanical rotation for example on a drone, to spin the blades and create lift. We find these motors used in PC cooling fans. This CD drive uses a brushless motor, and even this battery-powered drill also uses a brushless motor. What makes this different to a standard DC motor? When we compare the two, we can notice that both have magnets in the outer casing, and both have coils of wire at the center. However, with a standard DC motor, we find these brushes at the rear. This refers to the arms and the carbon blocks, which rub against the commutator plates and allow electricity to flow through the coils while it rotates. The gaps in the commutator plates cause the coils to energize and de-energize in a certain order to cause the rotation. Because the brushes rub against the commutator plates, they wear down over time due to friction. So the motor will need to be repaired or replaced. When we look at a brushless motor, there are no brushes.
By the way, do you know what DC stands for?
Direct current. I have a quick question. Do cars use DC? Actually, that doesn't make
Cars
sense.
use AC motors.
Oh, really?
Yeah, surprisingly.
Oh, okay.
Even though batteries produce DC, they first convert that into AC, and then they use AC motors because I think that produces less heat. I'm not very sure about like why.
Yeah, because I was thinking like for a car, like if it has brushes on it, that would be pretty like, especially if you're driving a lot. That needs like a lot of repairs. I mean, I'm not a car person. That was the first thing that came.
It will kill the motor.
Yeah.
That's because in this design, the outer casing rotates,
But
the coils
BLDC,
remain.
so if you're gonna use BLDC motor, BL stands for brushless. So there's no actually like point of contact like we just saw in here. DC motor is, by the way, like you just connect it to battery and it starts rotating. That's it. So DC motors are pretty simple. But BLDC are a little bit tricky to understand, but I'm pretty sure you will be able to understand it right now.
Great. As there are no brushes, there is very little friction, which makes the motor more efficient and it lasts longer. We can also get in-runner motors, where the rotor turns inside. But most applications use outrunner motors, where the rotor turns outside the motor. In-runner motors typically rotate faster, but outrunner motors have much more torque, which is why they are more commonly used. So we will only discuss this version in this video.
We're using adhesive. Neodymium magnets are extremely strong, so it was quite challenging to separate them. In this setup, I'm placing the magnets with alternating polarity.
So it makes a brushless
Once that's
motor
done,
from scratch.
the rotor is complete.
Right, from scratch.
Next, I'll prepare the stator. I'll wrap 20 AWG.
So you see, this is a single coil. So the hardest thing in motors today is like winding. To understand winding, you have to like just make sure that you see that this is a single loop here that you see on screen. So it is going here, it is winding up this stator, then it is carrying over to the next stator, and then it is going here, so on. This whole thing is one coil so far. If I were to like take these two strands and if I were to like straighten this up, this is a single wire so far. But now he's gonna add different cuts of wires. I think he's gonna add two more like this.
Wire to form coils. For deep
This is one more.
instructions on winding, please.
This is, so far we have done three coils, and those three coils will have 6 terminals, right? Because we had 3 wires, so how many free ends? Times 2, like 3 times 2. We have 6 free ends of the wires. What we do is we couple 2 of them together based upon their polarity, and this is to, you'll see what
The
actually
link in the
happens.
video description. Since I'm using a star connection, I'll remove the coating at the ends of the wires, solder them together, and then install the cover. Right now I'm using 20 AWG wire, but to reduce heat, I might switch to thicker 18 AWG in the future. Once the stator and rotor are ready, I'll test the motor. Using an inexpensive ESC, it spins smoothly. That means the basic motor structure is complete. Provide the precise angle control that's crucial. As you can see, it's running smoothly with no issues. However, while a low-cost ESC like this can handle basic speed control, it can't provide the precise angle control that's crucial for a robot actuator. To fully unlock a BLDC motor's potential, you need an ESC that supports more advanced control methods, like SVPWM.
Okay, this is the most important part. So remember how I told like there's three windings or like the three independent wires that has been mounted. We coupled two of those ends in such a way where we're only left with three free ends. So each of these free ends internally have two free ends in them. But like forgetting about like the winding details.
A BLDC motor has 3 signal lines, and by connecting each one to either VCC or ground, you can theoretically generate 8 different stator magnetic field patterns.
So think about it this way. In those 3 ends, those are independent 3 ends.
All those three are different colors.
Oh yeah, because these are 3 unique wires. We'll go up here first.
So like based on like the voltage, it like goes to a specific magnetic position that's like it's related to like the poles of where your brushless is.
So see this picture. If I gave the red wire a positive voltage here and a negative voltage here, there's gonna be current flowing like this here, right? And one thing we did not talk about in electromagnetism so far is if you have a coil of wire and if you have current passing in here, coming in and going out like that, then if the coiling is in this direction, meaning clockwise from my perspective, then there's gonna be some magnetic field generated by this. That magnetic field will be, if you curl like this, it will be pointing towards your thumb. So because it's coiling like that, this is gonna be a magnetic field because of this flowing current. So if I flow current here, there's gonna be a magnetic field. I'm just gonna draw with the same color for now. This. Let's call this B1 or B0. Okay? And there's gonna be one corresponding, if I pass current here, there's gonna be a magnetic field here. Let's call this B1. And there's gonna be one in this direction. Let's call this B2. Okay?
They're all perpendicular to each other, or just they're on that plane?
Oh, I've drawn the arrows.
Oh, okay.
They're in a plane though.
Okay, so not okay.
Yeah. So one thing like that is tricky to understand in this situation, since these are coupled, right? The red and the green one are coupled. So I can never have a situation where I only give the red one the positive voltage.
So the green gotta have it too.
Exactly. So I can never have a situation where I isolate the red one and give the positive voltage only to the red one. But the workaround is I can have a situation where I give positive to both, but give negative only to the red one. See? Because here there's black and red, not red and green again.
What does black correspond to? Sorry.
There are 3. Basically, think of it as like 3 different coils. And each coil have 2 ends. So we have a black coil, a green coil, and a red coil. And black coil has 2 ends, which are here and here. Red coil's ends are here and here. Green coil's ends are here. If I were to my question was, can I isolate B0? Can I have a situation where I'm only creating B0 and nothing else? Yes, I can. Here's what I'm gonna do. So I have only 3 free ends, 0, 1, and 2, let's call them. I'm gonna give some positive voltage here, and I'm gonna give negative voltage here. Now I've isolated the red, and nothing else is being powered. This is just a way to like reduce the number of free ends. Otherwise, like you will go crazy. Like there will be like 6 free ends. Otherwise, so this is you can still isolate them even though you couple the ends. That's like the beauty of making it simpler in terms of number of free ends. And that is also what adds complexity. Like it's beauty in disguise.
7:30.
Okay. Do you guys want to continue or?
Just try to figure out a way to round it up, and maybe we can like pick up next time.
This is winding.
Find something to eat.
So let me just like finish it, I guess. At least the B and DC now, since you started it. So if you I can isolate each of them. You agree or not?
Yeah.
Agree, right? Now let's say I isolated these two, B0 and B1. What will the sum of these vectors will look like? The sum of these two vectors will be pointing in this direction, right? Sum of these two vectors, B1 and B2 will be pointing in this direction. Sum of these two will be pointing in this direction, right? So I can, like from all the combinations, I can create a magnetic field on my will in any of these directions.
Oh, just using the coils. Basically.
Just using like which coil I want to power on, which one do I not power on. So this permutation combination allows you to point a magnetic field vector arbitrarily anywhere, almost. And again, we're gonna do the pulse width modulation here. Let's say I want to create a magnetic field here. There is no permutation combination of powering these 3 coils that can allow me to produce that. But at the same time, if I power this on for let's say in a compute cycle, if I power this on for, if I have this state for 0.5 of it clock cycle, I'm just gonna say C seconds, and if I power this on for the rest of the time 0.5 C seconds, then it will, if the frequency is fast enough, it will be just as if the magnetic field vector was pointing there. See, you see the magic.
From like digital to
Right.
analog. Yeah.
Right. I'm gonna change between these two states so fast that it will be as if my magnetic field is pointing there. And if I can achieve this and this, I can go between them too using the same logic and so on. And boom, like you can point a magnetic field anywhere. And now, like, if you remember, in the outer casing, so there's a casing where you place this whole core in, right? In this casing, there were magnets, just like I've drawn here, similar to this situation. And now, we remember that we can point a magnetic field anywhere, and we have this situation. Let's say our magnetic field vector is pointing here for now. It's kind of like in a neutral situation. There's north here, there's south here. Let's analyze the situation. Can you point the camera here, please? And this is like the final piece of the puzzle. You understood sensors, you understood microcontrollers. If you understood how to actuate things, how to move things in real world, that's it. These are the 3 components. There's this 4th component, which is software, but like we can talk about it like some other day. So let's just focus that in this casing. Let's say this is the casing of the motor, BLDC motor, and let's say this was the north, and this was the south. I'm not gonna draw anything in the south. This was again the north. Let's say this is the center. And if your magnetic field vector from the thing we just saw is pointing here, will that be facing any forces? What do you think? There's gonna be magnetic force, but will this be having any rotational force? Like, will this be rotated if B field is pointing here? What do you think? See, like, I'll just like make it clear. North attract south, and north, basically it's the same situation. Same poles repel, and the opposite poles attract. When I draw this, right, what do I mean by this is the magnetic field lines always come out of the north and go into the south. So for a standalone magnet, it looks something like this. It goes out of north, but it winds back, like coming into the south. So when I've drawn something like this, what that means is you can imagine that there is a magnet sitting here like this, and there is a magnet. Let me just use these caps. Let's say this is the north, the pointy, and the base is, let's say, the south. So this is the situation right now. It is in the neutral. It is in a neutral situation because this is south. This will be attracted by north, and this is a neutral situation. So no forces. But what if I, since this B vector, I can change it anywhere. What if I moved it here instead, in the middle of these things?
Or like you like switch it.
Yeah, I like physically
Go
move it.
to the right.
Yeah, because this is north, and north will repel. This will be shifted towards the left. What if I keep changing these B fields?
If you keep changing it at like a rate,
I will keep getting the repulsion, right? It will keep rotating, and I can, like, on my will, make it rotate.
So like when you only have that single one, like you don't change it, it stays in that same position. Like I mean, like
Yeah.
for example, if you just leave this and you don't change this, like you just leave this for like one time step, these will all stay in that same position.
Yeah.
Oh, okay.
It will eventually find an equilibrium, and it will stay there if you're not applying currents,
Oh, okay.
changing currents.
But yeah, it'll modulate before.
So like everything is now to like back to like the from where we started, pulse width modulation. If you can modulate the pulses for each of those three coils in the right sequence, which is the job of ESC, electronic speed controller, then boom, you can keep changing it in such a way where you're getting the repulsion between the magnets, and it is just keep rotating.
That's interesting.
And now, like, there's three abstractions to control. So now we have actuation. We don't have controlled actuation yet. Like, how do you think we can actually like control it? There's three philosophies behind it. First philosophy is controlling how much torque you're applying. Second philosophy is controlling where you are right now, like positional control. And the third philosophy is speed control, how fast you're moving. Depending upon, for example, in a propeller, speed is the only thing that matters. So you will design your controller with the philosophy of only caring about speed ever, never caring about where your propellers are pointing and stuff like that. If you let's say if you have an elevator, and if you want to design a control system for the elevator's motor, position matters the most, where you're pointing right now, and torque also matters. If there's a lot more people on the elevator, then you can not be applying the same small amount of torque that you usually apply. Let's say there are 10 people on the elevator. Now you have to apply 10 times as more torque. But if you apply that same torque for a single person, that person will be like shot up. You know, like the acceleration will be like too violent for that one person. So you have to like see, you have to like balance between these three philosophies to like achieve perfect control that you're looking for, depending upon the application. So for in our case, we have two of these. In the thrust vector control, where the rocket's direction is being changed, position is the only thing that matters. And in the BLDC motor, where we're controlling the thrust or the propulsion, the only thing that matters is the speed. So we're going to use a typical ESC and BLDC combo that we just saw for achieving the propulsion, electric propulsion, and we're going to use what is called servo motors. So this is just one type of motor. Like engineers are very creative. They have like a suite of different motors. One of them is called servo motors. Servo motors have inbuilt PID controller. We will talk about that in like some other day. But what it allows you to do, it allows you to position control. You can say, hey, go from 0 degrees to 45 degrees, and it will go perfectly to the 45 degrees, and it will stop there. It will not stop at 46, not 44. It will stop at 45. And if you, let's say, if it is an active control, and if you like wiggled it, like let's say you brought it to 40, it will like go back again to 45. So position control is what we have in the thrust vector system. And that comes from the servo motors that you see right here in the table. No, it's not that. V motor.
Oh. So those are regular DC motors.
No. These are servo motors. Position control. You can check them out. I think we stopped the recording.
You taking the picture?
It's a video, but we will like pick up the best frame.
Oh, just like screenshot it.
Yeah, we'll just screenshot it. Yeah. Just for like posting, as we're not posting enough.
We need to.
We're not posting at all.
Yeah.
We move in silence.
Unfortunately.
Let the action make the noise.
Dude, the underground.
The problem is action is all.